العالمين.
We can start to peel back a layer of simplification that we've been assuming for the past few weeks since week 1. So a string, recall, is a sequence of characters. And so if you want to create a string that says hi in all caps and an exclamation point, we do string s equals quote unquote hi. And we can hard code it like this, or we could use getString. But for now, just assume that I hard coded it into my code to always say hi in all caps with an exclamation point. Well, what does that look like in the computer's memory? Well, let's stop looking at the entire memory. Let's just focus on really what's going on. Once you create a string called s and store in it hi, you know that a couple of things are happening. H and I and the exclamation point are ending up in the computer's memory. We know from week 2 that this thing, the so-called null character, NUL, aka \0, is also being added for you. And it's somewhere in memory. At the moment, I don't really care where. I drew it at the bottom right. Yes, it has an address. But for now, it just ends up somewhere. And in fact, here's a little visual cue as to how this happens. In C, anytime you use double quotes to give you a string, you can imagine that the double quotes are like a clue to C to not only store HI exclamation point, but also put the null character there for you. And this is in contrast to what? Chars, if you want individual characters, what syntax did we use instead? So single quotes. Single quotes do not add magically a \0. They literally just store one character. So again, strings have always been a little special. You get an extra byte for free so that you know where the string ends. And functions like stir compare can then find their way there. So in memory, it might indeed look a little like this. And if we assume that there's going to be somewhere in memory, these things are going to be somewhere in memory, we can address them per week 2. By way of the name of the variable. So if s is the name of the variable, s bracket 0 is how you would refer to the first letter, s bracket 1, s bracket 2. And if you really want, s bracket 3 would get you at the null character at the very end. But what is s? So technically, in this line of code here, not only is the computer giving you memory for hi exclamation point \0, it turns out that s itself must take up some amount of space, right? Because s is the variable. And every time we've talked about variables thus far, I've given you a rectangle on the screen in which to store its value. So let's assume, for the sake of discussion, that the h is at 0x123, and I is at 0x124, exclamation points at 0x125, and the null character is at 0x126. Well, what then is s? Well, s is just going to be some other variable, and I'll draw it somewhat abstractly without all of the other boxes up here. And I'll claim that the name of this variable is s. But it turns out, what is s really? How do strings really work? Well, s is a variable and has been since week 1. But when you define it, what the computer is doing for you automatically is when it knows you want to store hi exclamation point, it puts that somewhere in memory. The computer then figures out for you what's the address of the very first character. And it stores that address, and only that address, in the variable you created on the left-hand side of the equal sign. And that's enough. Like, to represent a string with 3 letters of the alphabet or punctuation, you don't need 3 variables. You just need 1. You just need to know the beginning of the string. Why? Why is it sufficient for a variable to only store the first byte's address and not all of the byte's addresses? Exactly. Because of the design of strings per week 2, we always null terminate them. So it suffices to only remember the first byte's address, because from there you can sort of follow the breadcrumbs, byte after byte after byte. And until you see the new line, the null character, you know that all of those characters are apparently part of the same string. So this is what's been going on in the computer's memory all since week 1. And in fact, if we abstract this away, you can really think of s as being just this. Really a pointer to that chunk of memory. So in fact, what do we have here? Well, to recap on the code here, we have on the left-hand side string. That's what ensures that we'll actually be able to print out, store a string in a variable called s. We're going to have on the right-hand side, though, the actual value. So let me switch back to VS Code here, and let me change my code to no longer involve integers alone. Let me go ahead and let me do something like this. How about, let me go ahead and do perhaps this here. Yeah, let's just do something simple like this. So I'm going to add the CS50 library just so that I can use some shortcuts in there, CS50.h. And then in my main function, I'm going to go ahead and do this. String s equals, quote unquote, hi in all caps, exclamation point. And then I'm going to go ahead and print out, using %s as always, \n, the value of s. So this program at the moment, not interesting at all. It's just week 1 stuff again. /addresses indeed prints out hi. But it turns out that now that I know this, what's really been going on underneath the hood all this time? Well, here's that same line of code that defines the variable called s. And it turns out, anyone want to guess what string is actually a synonym for? String, it turns out, is kind of a white lie we've been telling since week 1. There is no such thing as string as a keyword in C. It's technically a CS50 thing, yeah? It's a pointer to a character. So really, all this time, we've kind of been lying to you. There is no string, quote unquote. It's actually char star. And if I may dramatically, here go the training wheels. Like, OK, that didn't land very well. So what have we been doing? Well, it turns out that string is a much easier way conceptually to think about what a string of characters is. Like, my God, if we had to start in week 1 by having you type char star, like, yeah, you might get past it. But like, this is just way too much ugly syntax, not intellectually interesting at all. So we abstracted away what a char star was in the first week of C by telling you it's actually called string. Now, string is a term of art. Like C programmers are in any language, will use the word string to mean a sequence of characters. But in C, it's not technically a word unto itself. It's rather a synonym that we ourselves created in some form. So in fact, how did we do this? Well, think back to just last week. Last week, I proposed that it'd be really nice if we had a person data type, which the creators of C did not think of decades ago. But that's OK. We can define it ourselves. What did we do here? Well, we're using syntax like this. Recall that we defined a person to be what? To be this structure. This structure, using the new keyword last week, struct, means that a person is just a name and a number. And it could have been other things. We just kept it simple. But how did I associate person with that structure? Well, we claimed that it was this value here, typedef, which, as you might expect, defines a data type. So what did we do as CS50 back in week 1 without telling you? Well, we could have done something like this. Like int itself is a little cryptic, and maybe we should have, to keep things even simpler, said, hey, everyone, turns out you can define integers in C. And if you wanted to do this, well, if you want to create the keyword integer as a data type, you can just typedef it to int. So typedef creates the word on the far right, integer, and creates a synonym for it, in this case called int. So what did we do in week 1 without telling you? We have a line of code like this in the CS50 library that associates quote unquote string with, more cryptically, char star. And this is why in week 1 onward, anytime you use the CS50 library, you can write the word string as though it's a real C data type. And that's just because we wanted to have this abstraction, these training wheels on for the first weeks, so we don't have to get in the weeds of all this crazy memory stuff. We can sort of talk about strings at a higher level. But that's all they are. Strings are the address of the first character in that sequence of characters. Questions now on any of these details? Yeah? Good question. What about the strings library, which we have used? Unrelated. So it does not define the word string. Everything in there actually relates to char stars. And so in fact, if you've used the CS50 manual, which is just our user-friendly version of the actual manual pages for the official language C, you'll see throughout that now, if you start poking around or turning off less comfortable mode, you'll actually see that we've changed any mentions of char star in the official documentation for these first weeks to just string, to simplify it. But underneath the hood, C does not know the word string per se as a keyword, but it's absolutely a concept that like every program in the world knows about. And in fact, in other languages, in Python, for instance, there will actually be a proper string, although it's not going to be called string. It's going to be called str, S-T-R for short. Questions on these strings here? Questions just yet? Well, let me propose there's one other feature of this syntax that we can now leverage as follows. Let me propose that if we go back to the previous version of my code here, wherein, let me switch back to VS Code in just a moment. I'm going to rewind in VS Code to the integer version of my code from before. And most recently, it looked like this. Before, when we were using integers only and not, in fact, strings at all. Let me propose that there's this other feature of C that we can use that actually allows us to go to an address. So at the moment, let me just rewind and do make addresses to remind you what this program did when it was using integers alone. And there's that address. Why? Because on line 7, notice, I'm printing out the value of p, which is a pointer. So of course, it's going to look like an address. But let me zoom out now and make one change. Instead of printing out p, how can I use today's second new operator, not the ampersand, but the star, to actually go to that address? Well, what I can actually do on this line of code is this. If I want to print out the actual integer 50 that's in that variable, or equivalently at that address, I can go to p here and not print p literally, because that's just an address. I can now say star p. And star p means go there. More technically, dereference p. That is, follow the treasure map to the actual address and do what Carter did, open the mailbox and print whatever was in the mailbox, which recall was the actual number 50. So let me try this. Let me recompile the code. So make addresses. OK, let me clear my terminal window. /addresses. This time, I shouldn't see the OX anything. I should see just the number 50 in this case. And here, too, is kind of an unfortunate design decision. Certainly pedagogically, I would say in C. If I zoom in on this code, star is unfortunately being used in 2 different ways. In an ideal world, they would have used 3 different symbols to make this more semantically clear. But this is what we're stuck with. So in line 6, when you declare a pointer, that is a variable that stores an address, you put the type of variable that you want to point at, then a star, just because, and then the name of the variable. And then on the right-hand side, you actually get the address of whatever using ampersand. But when you want to go to an address, you want to dereference a pointer, you don't use int again. And we've never done that, right? Once you declare a variable, you never again mention the data type. But in the world of pointers now, if you want to not print out p, but go to whatever address p is storing, you use star p here. So a good visual indicator would be when you declare a pointer, that is, make it exist in your program, you have to declare the data type with the star. But when you use a pointer, you just use the star. In an ideal world, this would be a completely different symbol. But again, this is what we have. Questions now on that syntax? Yeah? Sorry, a little louder. Why can't we just do the ampersand here, are you saying? It was still a little quiet. So strictly speaking, we do not need line 6. So this is really for pedagogical sake that I am defining a separate variable p and then printing it out. At this point, though, I'm just kind of going in circles, if you will, because more simple would have been what I would have done in week 1, which would be get rid of p altogether, get rid of p here, and just print out n, right? But today, we're just giving you this new building block, this new syntax, via which you can figure out the address of something and then reverse the process later and actually go to it as well. Other questions on what we've done here with these pointers? All right, well, let's context switch back to the string now and see what more we can do with this here. In the case of our strings here, let me refine this to zoom out. Let me delete the integer related code here. Let me do string s equals quote unquote hi in all caps. Let me go ahead and for the moment include CS50.h at the top so that indeed I can use the keyword s, or string rather. And let me go ahead now and do something more than I did last time. Last time I did printf of %s\n, and then I printed out s. And again, I'll recompile this just for clarity. Make addresses, /addresses, that just prints out hi. So that's, again, week 1 stuff. But now that we have this other bit of syntax, we can do some interesting things too. So for instance, suppose I want to print out not s itself, but what if I want to print out the address of s? Like at what memory location is s? Well, I can change my %s to %p, which now we know p is for pointer. So %p means print out the value of a pointer. That is an address. And here, I can actually print out s itself. But why that is, we'll see in a moment. Let me do this. Here go the training wheels. String does not technically exist, but it does if I'm using the CS50 library. But if I get rid of the CS50 library, as I'm metaphorically doing by taking off the training wheels, I can't use the word string anymore. And in fact, let me make this mistake deliberately, as you might have accidentally in past weeks. Here's the error message I get if I forget the CS50 library. Use of undeclared identifier string. Did you mean standard in? It's trying to be helpful, but it's not, because I didn't mean standard in. So indeed, this is confirmation that C does not know the word string exists, at least as a keyword. Exists as a concept, but not a keyword. So I could fix this by adding back the CS50 library, but that's kind of a step backwards educationally as instead of a step forward. What could I do instead to fix this now, if the training wheels are now off? Yeah. Exactly. Replace string, quote unquote, with char star instead. So I'm going to go ahead and change this to char. Technically, you can put the literal star here, the asterisk, or you can put it there, or you can put it here. By convention is to do what I'd done from the beginning. Put the star next to the name of the variable as opposed to anywhere else. Let me go ahead now and sorry, I meant to add the spaces there. You could do this too, but this would be the most normal convention. So now let's do this. Make addresses. Compile's OK now. / addresses, what should I see? Hi or something else? Feel free to just call it out. So still hi, you say? Someone else? A memory location. All right, so it could be one of the two options, right? Either I'm going to see the string or I'm going to see a memory address, though I do in fact see a memory address, and this one's quite different from the integer one. But does anyone now want to explain why you were correct? Why am I seeing the address down here and not hi? It's subtle, yeah. Exactly, because I left my %p there, which means, hey, printf, show me a pointer. But this is where printf is smart and has been smart since week 0. Humans who invented printf decades ago wrote code that notices that, OK, %s means to treat the following value, not as just an address per se that gets printed literally, but print it, as with the mailbox demo, as sort of a treasure map that leads you to the address of a character. So simply by changing one character, %p to %s, and if I now do make addresses again and / addresses, this now is identical to week 1, but hopefully makes sense because %s is just a clue to printf that means go to this address in s, we'll print out every character there and thereafter until you see what? The null character, and then stop printing anything more. And this is why hi has printed since week 1. Today we can see the address %p, but this combination of having access to addresses and the null terminator is all the information printf needs to actually do something more useful by like printing the actual strings. Any questions now on this approach to %s? Any questions? Yeah, in back. So if %i is for integers, why is %s for strings? Oh, so why is it traditionally being used in this way? Honestly, like the word string has been around for decades. It's not a keyword you should be able to type in C unless you're using a library like CS50s. And so %s just means string. So even though it doesn't exist as a keyword, %s connotes string. And humans decades ago, like today, just kind of know what that means. So they could have chosen any letter of the alphabet, but S sort of makes the most sense. All right, well, let's in back. Other question? Good question. Before, let me zoom in. I did not use a star before the S. Why? Well, it's subtle here, but printf was invented years ago to know, given an address, like in the variable s, printf knows to go there. So if we looked at the source code that some human wrote years ago for C, we would likely see the actual asterisk that you're referring to. Printf is taking on the responsibility for going to S. If you were to do star S here instead, an asterisk and then S, that would now be literally a character. Because if I say star S, that means go to the address in S, and all you're going to find there is a single character. What printf wants to know is not what is the character there, what is the address of that character. Why? Because printf needs to walk through the rest of those characters looking for the final null character. And in fact, let me see with a bit more syntax if we can highlight this a bit more. Let me do this. In addition to printing s, let's try out our syntax in another way. Let me print out with %s. How about not s here, but let's print out some addresses. %s, \n, close quote, and then let's print out, how about this? The first character in the string s would be called s bracket 0. But how do I get the address of the first character in s? Well, I could technically just use today's new primitive. I can just add an ampersand. That always gives me the address of some value. So when I end this thought and clear my terminal window and run make addresses, still compiles. When I run addresses in just a moment, any guesses as to what I will see line by line? This will print out two things. And you don't have to remember what the actual number was. But at a high level, what will be printed now? The same thing twice. Why? Well, when I run this, what I'm printing here, and let me zoom in at the bottom, I indeed see two really long addresses, but they're in fact the same. Why? Well, that's because, again, if s is the address of a character, as implied now by either the CS50 word string or the actual phrase char star, well, then s is just an address. By contrast, per week 2, s bracket 0 is a char. Always has been a char, a specific char. But if you want the address of that char, you just add the ampersand. Well, it turns out that strings, per the definition we keep emphasizing, is just the address of the first character in a string. So of course, if you do this, you're going to see the exact same thing. And if I do this a bit more, generally you don't want to copy paste, but this is just for visualization's sake. Let me print out all of the characters. So another, and let me change this to print out the address of bracket 1, bracket 2, and bracket 3. So all 4 characters, HI, exclamation point, and the null character. Notice I'm using %p for all of them. So if I now do make addresses and /addresses, now notice, and this is kind of cool, the first 2 are indeed still the same. But what's noteworthy about the other values on the screen? Yeah, they're consecutive. Each of these is just 1 byte away. Even if you're not good at hex yet and there's a crazy number of digits here, who cares? They're all the same except for the last ones. 4, 4, and then 5, 6, 7. And this confirms what I've been claiming for weeks, is that in an array, all of the characters are back to back to back, contiguous, 1 byte away. So with just this ampersand, with just this star, like, it's actually a pretty cool tool in the toolkit to have, because you can start to poke around what's actually going on inside of the computer's memory. And in fact, if we do this, I can introduce one other cool trick here, if you will. Let me propose that, and I'll pull up a visual here in just 1 second. Let me propose that we can actually now do arithmetic on pointers. And you don't have to. You'll see a simpler way to do this. But now that you have perhaps this underlying understanding of where things are in memory, and it's just addresses, we can actually do something kind of neat. We can do something like this. Let me go back to, how about the string version of this with high. And let me do this instead. Let me clean this up a bit, get rid of some of these lines of code. And let me do this. Let me print out %c, %c, %c. Let me get rid of all these ampersands. We're going to roll back to like week 2 stuff. Just to be clear, when I compile and run this version of the program, and I'll zoom in, what should get printed on the screen? This is just week 2 stuff now. No pointers per se. Yeah? Just HI exclamation point, 1 per line, because I have all of these \n. So let me do that. Let me go down here, make addresses, enter. OK, pretty good, /addresses, and indeed HI exclamation point. But now, if you're getting a little more comfortable, and it's fine if you're not yet today, but over the coming week or weeks, as you get a little more comfortable with the equivalence of addresses with our definition in the past of arrays and strings and all of this, you can start to play around. And I can do this instead. If I want to print out the first character in the string, I could do, like week 2, s bracket 0. Like, that will always work, and you can keep using that. That's not a CS50 thing. It's just a convenience in C. But I could technically print out not s, because s is an address, but what would be the syntax I could use to say print out the character at s? Any instinct? How can I say go to the address in s? It's one of 2 possible answers today. A little louder? Yeah, is that in back or? OK, let me come back to you in just 1 moment. So of our two new operators today, we have the ampersand and the star. Which one will lead us to what is at an address? So the star. So in fact, if I want to print out what is at address 0, at the address S, I can just do star S. And if you really want to get fancy, how do you print out the second character that's immediately to the right of it, so to speak? Well, you can go to, with the dereference operator, and do you want to answer this one? S plus 1. Ergo pointer arithmetic. Like you can do math, simple addition, subtraction, whatever, on pointers if you want. And you can do this here too. So star, if you want to pluck this one off too, how do I print out the last character, the third? S plus 2. Right? Because if you know and understand that like a string is just a sequence of characters, every character is just a byte, and these bytes are back to back to back, you can just go wherever you want in the computer's memory. And here, I can do make addresses again, /addresses, and voila, we now have high exclamation point. So we haven't printed out anything new, but again, just by using these two new operators, the ampersand and the star, you can figure out the address of something, and you can go to the address of something. OK, question in back. Indeed, it ends up being the exact same. And so I might have used this term before, the ampersand technique, the square bracket technique where you do S bracket 0, S bracket 1, S bracket 2. That's actually what we would really call syntactic sugar. Like it works and you can use it, you should use it, it's nice and simple. But the square bracket notation underneath the hood is essentially being converted to this, which this is not fun, right? Like this is when you want to show off to your friends, like you know how to do cool stuff in code. But this is not as readable as just S bracket 0 and 1 and 2. But that's all that's happening underneath the hood. And so again, this is why in CS50 we spend time on some of these lower level building blocks, because if you assume that indeed your computer's memory is just this grid of bytes, and you have now the code ability in code to get an address and go to an address, you can start doing anything you want. And you can poke around a computer's memory at any location. And herein lies the danger. Like I'm kind of on the honor system right now that if my string is high, exclamation point, it's kind of up to me to go to the first byte, the second, and the third. But I could get kind of crazy now. And if I want to see what's going on in the computer's memory, I mean, there's nothing stopping me from doing like S plus 50. And let's see what's there. So make addresses, /addresses, high, and then, OK, nothing, it seems. Well, how about 5,000 bytes away? Let's just poke around. What's inside of the computer's memory? So make addresses again. Make addresses, /addresses, enter. OK, still nothing there. Let's try 50,000. All right, make addresses. /addresses. OK, there we see it. So you've probably done this, some of you, by accident, because you probably went too far to the left or to the right in an array, touching memory that you shouldn't. Suffice it to say, I should not go blindly touching 50,000 bytes away, because who knows what's there. And indeed, in your computer, when a program is running, the computer segments it into different segments of memory. And if you get a little too greedy and you touch another segment of memory that technically was not allocated to you by Mac OS or Windows or Linux or the operating system, bad things happen and you get a segmentation fault. And that means it's a bug in your code. So you can now do this. And this means hackers, too, can do things like this. If they can somehow inject code into your C program, maybe they can poke around the computer's memory. And indeed, this is kind of the technique whereby maybe a really sophisticated hacker can jump to this memory, this memory, this memory, looking for something like your password or your financial information or anything that's in the program but at some other address. There's nothing stopping an adversary, at least right now, from poking around, if they can execute code on your computer, from doing this kind of thing. So there and again is the power of C, but also the danger. And you'll absolutely suffer more seg faults in the coming days. But ultimately, the goal is going to be to help you solve them ultimately and fix things. But for now, I think that was quite a bit. So let me propose that we go ahead and take our longer break here, maybe 10 minutes, and have ourselves some whoopie pies and the transept. We'll be back in 10.